Okay, let's dive right in. Have you ever looked at a massive skyscraper or maybe a microscopic circuit board and wondered, how do the people who actually build these things know exactly what the designer intended? Well, welcome to today's Explainer, where we're going to unpack the absolutely fascinating world of engineering graphics. We'll be looking at how creators all across the globe communicate the invisible rules behind literally everything we use, build, and manufacture. Seriously, think about it for a second. How does an engineer sitting in Japan perfectly interpret a complex design from a team in Canada, especially when they don't even speak the same language? Have you ever wondered how global manufacturing is even possible when the teams involved are separated by oceans, distinct cultures, and entirely different alphabets? It sounds kind of impossible, right? Well, the answer to that is engineering graphics. Now, to be clear, this isn't about artistic drawing or subjective interpretation. Not at all. It's a strict mathematical visual language. It's carefully governed by international bodies like ISO and BIS. And why? To ensure absolute manufacturing precision without a single drop of ambiguity. When you're speaking this language, there's just no room for guesswork. Every single curve, line, and angle holds a precise, undeniable meaning. So, here's our quick roadmap for today. We'll start with the universal language, move on to the engineering canvas, then the alphabet of lines, projecting 3D to 2D, and finally wrap up with the digital evolution.
All right, section 1, the universal language, the foundation of design.
If we break it down, unlike a beautiful painting, where the main goal is emotional expression, engineering graphics is all about absolute technical accuracy. It is the literal foundation for communicating complex ideas, whether you're designing a tiny internal watch mechanism or a massive suspension bridge. And standardization, that's the key to the whole shebang. Because it's governed by strict international standards, a specific gear manufactured in India is going to perfectly, seamlessly fit into an engine block cast in Germany. That is the raw power of a true universal visual language.
Moving on to section 2, the engineering canvas, setting the stage.
So before modern computers came along, essential tactile drafting tools were how the magic actually happened. You had these large drawing boards, T-squares, and this absolutely incredible device called the mini drafter, which brilliantly combines a T-square, set square, and protractor all into one moving tool. Historically, engineers used these along with precise compasses and very specific grades of pencils to ensure absolutely perfect parallel lines and measurements. It was a wildly meticulous, hands-on process that required intense focus and a really steady hand. And those precision tools weren't just used on random scrap paper. They were used on highly standardized sheets dictated by BIS and ISO standards. We're talking everything from the massive A0 sheets, which stretch 841 by 1189 millimeters, perfect for those sprawling large blueprints, all the way down to A3 sheets used for smaller subassemblies. Every single size has a designated, standardized application in the industry, which ensures that filing, storing, and mailing these documents is universally consistent. Now here's a magical little mathematical secret behind those paper sizes. Have you ever noticed that if you fold an A0 piece of paper perfectly in half, you get an A1? Fold it again, and you get an A2? That happens because of the square root of 2. It's known as the golden rule of aspect ratio. Every single ISO paper size maintains this exact width-to-height ratio. This brilliantly illustrates how engineers plan for efficiency because it lets you scale designs up or down between paper sizes without ever distorting the visual proportions. It's just pure genius. To finish off our canvas, every single sheet features a title block. You'll always find it sitting exactly in the bottom right corner, standardized to exactly 170 by 65 millimeters. You can think of this as the document's crucial identity card. It holds the drawing's title, the unique drawing number, the name of the designer, the mathematical scale used, and the symbol of projection. Basically, if you find a blueprint sitting on a desk, this block tells you everything about what you're looking at, who's responsible for it, and exactly how it connects to the broader project. All right, section 3, the alphabet of lines, grammar, and punctuation. In English, a comma or a period completely dictates the flow of a sentence, right? Well, in engineering graphics, line thickness and style do the exact same thing. Continuous, thick lines are prominent. They clearly shout visible edge and outline the physical object. But dashed, thin lines, they kind of whisper hidden contour. They represent edges, holes, and features that are hidden from your specific viewpoint, but they absolutely still exist inside or behind the object. Mixing these up is literally like misspelling a crucial word in a legally binding contract. And this standardization doesn't stop at just the lines. Even the lettering is highly regulated. Engineers universally use a standard font called single-stroke Gothic.
While vertical letters are standard for main headings, engineers will very often use text slanted at exactly 75 degrees for specific annotations. Even the height of the letters is strictly controlled, usually varying from 2.5 to 10 millimeters. This ensures that no matter who is reading the print across the globe, it's totally legible and completely free of any individual handwriting quirks. So, you might be wondering, how do we fit a massive airplane wing or a microscopic watch gear onto these standardized pieces of paper? Well, engineers use something called the representative fraction, or RF. It establishes precise reducing or enlarging scales. A full scale is exactly 1:1, meaning the drawing matches the object perfectly. A reducing scale, like 1:5, is used when the object is much larger than the drawing canvas. And an enlarging scale, like 10:1, blows up tiny objects so the manufacturer can actually see those minute details. It's essentially the mathematical bridge between the drawing board and the real world.
Let's jump to Section 4, Projecting 3D to 2D, Writing Complex Sentences.
To do this translation effectively, the absolutely crucial point is mastering orthographic projection. This is the global industry standard 2D multi-view system. Basically, it takes a complex 3D object and breaks it down into individual, flat views from different directions, specifically looking at the front, the top, and the side. By completely eliminating perspective distortion, this provides the exact true dimensions and shapes necessary for manufacturing. It creates those classic plan, elevation, and section blueprints that builders rely on so heavily to construct things safely and accurately.
Let's look at how this builds conceptually. To create these views, objects are projected onto two main intersecting reference planes, the horizontal plane and the vertical plane, which cross at what's called the XY line. The front view is always projected onto the vertical plane, and the top view goes onto the horizontal plane. But here's where it gets highly technical. Depending on where the observer is standing, positioning the object in one of the four intersecting quadrants completely dictates how those views are oriented once that 3D space is unfolded flat onto a 2D sheet of paper. This actually introduces a major, complex distinction in global manufacturing: first angle versus third angle projection. In first angle, which is the ISO standard largely used in Europe and India, the object sits between the observer and the plane. This results in the top view being drawn below the front view. But in third angle projection, the ASME standard used in the USA, Canada, and Japan, the plane is between the observer and the object, so the top view is drawn above the front view. Knowing which angle you're reading is absolutely essential. Otherwise, your part is going to be manufactured completely upside down.
Of course, sometimes looking at multiple flat 2D views is just a bit too abstract for a client or builder to grasp. So engineers also use isometric visualization. This is a 3D pictorial representation drawn perfectly to scale. To achieve this illusion of depth on flat paper, the horizontal axes are drawn precisely at 30 degrees to the base. It utilizes a specific isometric scale factor of about 0.816. This creates a highly realistic spatial orientation of the object, so everyone can instantly understand what's being built without having to mentally stitch those 2D orthographic views together in their head.
And finally, Section 5, the digital evolution, modern translation tools. The evolution of these tools is just absolutely incredible to look at. We started back in the 1900s with entirely manual drafting boards and T-squares. By the 1980s, the revolution hit with 2D CAD softwares like AutoCAD, bringing total digital precision to the table. The 2000s pushed boundaries even further with 3D parametric modeling, using tools like SolidWorks and CATIA. And now, in the 2020s, engineers are collaborating inside of digital twins and full virtual reality simulations. The software has become unimaginably powerful, but you know what? The core language, those foundational rules of projection, scale, and precision, remains completely unchanged. Which leaves us with this really powerful thought. Design is not just what it looks like and feels like. Design is how it works. Whether you're painstakingly using a pencil on a massive A0 sheet or collaborating inside a VR simulation, engineering graphics is the bridge between a wild idea and physical reality. So, the next time you step into a towering skyscraper or hold a perfectly crafted piece of technology in your hand, ask yourself, could you write the visual code that brought it to life?